All right, good afternoon, everyone, and welcome. We'll get started in just a minute, but before we do, just a few notes. We are recording this event and we'll be posting the video on the Basic Science website. So if you'd like to revisit the presentations or share with others who might be interested, this video and the other events in the series are all available for viewing on the Basic Science website. Due to the large number of attendees, which we're thrilled about, we're going to keep you all muted during the event just to minimize background noise. But we would like to hear from you. So if you have questions for any of our panelists, please post them in the chat. We'll try to get to as many of those as we can. And without further ado, it's my pleasure to introduce the Dean of Mathematical and Physical Sciences, Richard Allen.
Great. Thank you, Susan. Well, good evening, everybody, and welcome back to Basic Science Lights the Way. As Susan just said, I'm Richard Allen. I'm the Interim Dean of Mathematical and Physical Sciences, and I'm really pleased to kick off this series of talks this spring semester. I don't know about you. I think we have a lot of people who come to each of these. I really have been enjoying these over the fall semester. The topics are always really interesting and exciting. It's a real inspiration at the end of the day. So I hope you all are going to enjoy tonight's as much as the previous events. And of course, the reason we do this is that they feature one of Berkeley's great traditions and one of our great strengths, and that is basic science research. So the goal of this series is to shine a light on how scientific discoveries are made and what it means to be driven by curiosity. So when we talk about basic, we don't mean simple, but we mean foundational. And when it's foundational, it can lead to transformational discoveries. So we find these foundational research sometimes leads to paradigm shifting discovery, and that's what we want to focus on. At Berkeley, we often point to well-known examples of discoveries that were made because our scientists followed their curiosity and their questions. Things like immunotherapies for cancer, CRISPR that we're all now familiar with, of course, the accelerating expansion of the universe, and of course, my personal favorite as an earth scientist, understanding how a meteor caused the great mass extinction. And so, of course, it's this last example that we are going to focus on today, what's often thought of as what killed the dinosaurs. This was Berkeley research done by the late and great Luis Alvarez and his son, Walter, who is a colleague of mine in the Department of Earth and Planetary Science. And I am delighted that Walter is here with us tonight to hear the talks that we have being presented. So tonight we're going to continue on that theme with current research that's being done to learn even more about that particular mass extinction event, as well as other ancient climate catastrophes. So while we can learn from these events, and they do relate to climate change that we are now experiencing, and what we're going to focus on and hear about today is great shifts that occurred many epochs ago in other worlds as we go back along the geologic timescale. So another reminder, once we get underway, we're going to encourage you to post your questions for any of our speakers in the chat box, and we will do our best to answer as many of these questions as we can. So please don't be shy with your questions. So on to the main event, onto our speakers. First of all, our moderator this evening is Dr. Lisa White. She's a geologist and the Director of Education and Outreach at the UC Museum of Paleontology. Dr. White is a former professor of geoscience and associate dean of the College of Science and Engineering at San Francisco State University. She's an elected member of the California Academy of Sciences and a fellow of the Geological Society of America. Lisa's interests span micropaleontology research, STEM education, and science outreach. Her career combines research and mentoring with a passion for expanding access to geosciences. So she is just the perfect moderator for today's event. So with that, over to you, Lisa.
Great. Thank you so much, Richard. And it's a pleasure for me to participate in today's event. And I'm thrilled to introduce this audience to some of my colleagues and their work. Each of the talks today will highlight the connections between extreme climate and their environmental consequences. The examples they highlight will draw from the record of deep time and raise fundamental questions about the relationship between Earth's climate and extinction in the past and also life today. So today we're going to hear from three inspiring faculty members, Nick Swanson-Hysell, Seth Finnegan, and Paul Rennie. They will talk about ancient climate and mass extinctions, and we really hope you enjoy these enlightening presentations about our planet's past. At the end of each talk, we will try to address all of the questions from the audience, so please do add questions to the chat. Our first speaker is Professor Nick Swanson-Hysell, and he is an associate professor in the Department of Earth and Planetary Sciences at Berkeley. His research focuses on understanding the geological record and long-term drivers of Earth's climate. Many of the research projects in his group focus on global change and also tectonics on ancient Earth, including the formation of ancient supercontinents. In his teaching, he's very passionate about inclusive field geology instruction, especially instruction that promotes critical thinking in the context of inquiry. In 2020, Nick was awarded the Noyce Prize for Excellence in Undergraduate Teaching. Nick will be elucidating the mysteries of Snowball Earth glaciation and the long-term controls on Earth's climate. I'm sure you'll enjoy his presentation. So over to you, Nick.
Thanks, Lisa. So I'm going to be talking today about how we can learn about Earth's past from the geologic record. So if you were a student in my Earth and Planetary Science course, Stratigraphy and Earth History, you would go to Death Valley over spring break, and you'd be tasked with walking this ridge line, going from these gray rocks up into these brown rocks, and making connections from the observations you're making to ancient environments. So for example, on those gray rocks, you would see limestones and you'd see these sphere-shaped structures. And being an astute Berkeley undergrad, you would connect those structures and that limestone back to lectures where we talked about how they can form, how they can be precipitated out of shallow, warm marine waters, like those shown in this image of the Bahamas today. Going further along that ridgeline, you'd encounter those brown rocks, and then you'd see that they're made out of muds, but with big boulders that have been dropped down into them. And you would think back to lectures where we talked about how this could happen if you have glaciers that pluck up rocks, bring them into the ocean, and drop them out into marine muds. So you would have made your own observations from these rocks, connecting them back to ancient environments and seeing that there was a major transition from a warm climate to a cold climate in that place in the ancient past. And there'd be a number of follow-up questions. When did this happen? Where did it happen? Why did it happen? So if we look through the geologic record and as well as climate models, there are three main climate states that emerge: a finite ice cap, a non-glacial climate state, and a snowball climate state. This is the one I'll focus on a bit later in the talk. So the finite ice cap climate state is the one we're in today, where there are ice sheets on Greenland and on Antarctica. They've gotten bigger and smaller over the past few million years, such as if we go back 18,000 years ago to the last glacial maximum, when an ice sheet covered most of Canada. But if we go further back, 50 million years ago, there's a non-glacial climate state without those ice sheets. It's like temperatures of San Diego in the water near the poles. And if you're near the equator, the ocean's as warm as a hot tub. But if you go back 700 million years ago, the Earth is fully glaciated such that even at continents near the equator, there is a Greenland-like ice sheet. So here's a compilation we've put together looking at the extent of ice sheets through time. So the latitude from the pole to the equator, looking over the past 1,000 million years, that is the past billion years. Today, we're in this finite ice sheet climate state. In Paul Rennie's talk at the end Cretaceous mass extinction, Earth was in a non-glacial climate. Seth Finnegan's talk will talk about how climate change leading into a glacial climate 450 million years ago. And I'll be talking about a period of Earth history 700 million years ago, before the evolution of animals. So Earth's climate on long time scales is largely set by the concentration of CO2 in Earth's atmosphere. On long time scales, that we can think about the sources of CO2 being that's coming from volcanic emissions. Now, these cycle through different reservoirs in the ocean and atmosphere, but ultimately lead largely through a process of rock weathering. So how does that work? So carbon dioxide can dissolve in rainwater, making it slightly acidic, and that can break down rocks into their constituent chemical components that can be delivered to the ocean and then precipitate out as rocks, like those limestones that the students look at in Death Valley. Ultimately, this can take CO2 from the atmosphere and sequester it as a rock. This process can balance out how much CO2 is in the atmosphere. More CO2 in, higher CO2 levels, warmer and wetter, enhanced rock weathering, more CO2 out, achieving a balance. This balance takes a long time, ultimately a balance that will balance out the CO2 that humans are putting into the atmosphere, but on hundreds of thousands of year timescales. So here we're looking at the ice line latitude, the extent away from the poles, and CO2 levels with respect to the present. So here we've gone back and forth over the past few million years with ice sheets waxing and waning. But what can happen, and we know has happened a few times in Earth history, is as ice sheets grow and go further towards the equator, Earth becomes more reflective. More of the incoming solar radiation is reflected back, which then cools the Earth, and ice sheets grow, becomes more reflective still. And this is what we call an ice albedo runaway, which leads to a snowball Earth with ice sheets all the way down to the equator. This was seen in really early climate simulations, but it was deemed to be impossible. How would you ever get out from this frozen reflective ice ball climate? But the process we just talked about with the carbon cycle provides a way out. The CO2 continues to come in through volcanism, but the rocks that could ultimately remove it and sequester it away are covered by ice, such that CO2 can accumulate some more until you can have an extreme greenhouse melt back to a non-glacial climate state. So we've been seeking to gain more insight into the onset of one of these snowball Earth events through researching rocks that are exposed in northern Ethiopia that were deposited in the ocean leading up to one of these glacial events. This has been working with my collaborator Mulugeta Renne, a professor at Addis Ababa University, and students of his, such as Mulubrahan Grabasolasi. And this work formed a substantive component of Park's PhD thesis. So one of the discoveries we made is that there were extensive additional exposures of these glacial sedimentary rocks recording this climate, and many places where we could see the transition into those glacial sediments. This geologic map that was constructed formed part of a senior undergraduate thesis research project here. So similarly to in Death Valley, we collect data going through the rocks, and we can see that we go from a warm environment and then abruptly transition into glacial sedimentary rocks, recording this abrupt climatic transition. So where did it happen? Well, continents move through time. So here, Ethiopia was near the equator at that time, as was Death Valley. So here in pink is North America on its side. And this is where we're seeing these glacial sedimentary rocks. So we have glaciation, ice sheets at low latitudes that were global in extent. So when did this happen? And one of the things that's been fantastic about our studies in Ethiopia is that there are many volcanic ashes that erupted into the ocean, contain small uranium-containing minerals that we can analyze and date as a geochronometer. So these give us precise ages, such as 719.7 plus or minus 0.5 million years ago, enabling us to tell time. So here we've discovered, comparing these new dates we've generated from Ethiopia to constraints that exist in North America, that glaciers arrived at the equator in both Ethiopia and North America at the same time, 717 million years ago. This rapid synchronous onset is what is predicted by the Snowball Earth hypothesis, and it's the first time it's been shown. So why did it happen? This has been a major research trajectory in our group, trying to understand what sets Earth's climate state on these long timescales. So here we're looking over the past 500 million years, and we see the extent of ice sheets through time. And what we've found is that when we're in a glacial climate regime is at times when there are extensive mountains made of rocks with high carbon sequestration potential in the warm, wet tropics. So that's shown here with the length of these different mountain belts. And you can see how well these peaks match one another. So we're able to do this because we have these reconstructions of how continents have moved through time, this being shown animated for the past 500 million years. We're now in the supercontinent Pangaea that's going to break up and bring us to our geography of today. And as a quick snapshot from this, from the time period that Seth Finnegan will be talking about, this is a time where there are abundant mountains with these rocks with high carbon sequestration potential that could soak up that CO2 and lead to a glacial climate. So we have a hypothesis that is a similar process was at play with extensive such mountains building up within the tropics 720 million years ago. There's many different directions that are needed to test this hypothesis, but one of them is to build up better reconstructions of how the continents have moved through time as we go into these more ancient periods. And this is a major focus of our research group, where we measure the magnetization of rocks, which act like ancient compass needles and allow us to make these paleogeographic reconstructions, which may allow us to test hypotheses about how these changing continental positions can lead to these long-term changes in Earth's climate through time. So thanks, and I'm looking forward to these other talks as we move forward in geologic time towards the present.
Nick, thank you so much. That was terrific. And I'm especially impressed with just the multiple tools and approaches that you use, and just how much you've been able to spotlight what additional things we're learning about that time. Can you just share a little bit more about some of the challenges and opportunities or doing field work in Ethiopia? What was most memorable?
Yeah, so it's been quite an opportunity to go and work there. I just feel grateful for the work we've been able to do for the research program over the past decade. Of course, international fieldwork has been challenging during the pandemic. So I've been grateful that I've been able to work with students on domestic research projects. There's additional challenges now, and unfortunately with internal conflict in Ethiopia, which poses an additional challenge.
I bet. And I'd like to draw a question from the chat, and a member of the audience asks, what are the types of rocks that can sequester carbon dioxide?
Yeah, that's a fantastic question. So in particular, rocks that are rich in calcium and magnesium are the ones that can then precipitate out and sequester that CO2. And those are rocks known as basalt. And one of the ways that they can form in particular is a lot of the oceanic crust is made up of basalt, as are places that you get a lot of basalt in places that are volcanic arcs, so like around the Ring of Fire, if you've heard of that. You get different types of volcanic rocks, but some of them have more calcium and magnesium. And so it's particularly those types of volcanic rocks that when they collide and make mountain belts have the particular sort of ability to sequester more carbon through that rock weathering process.
Great, great. Well, I'll ask one more. Daniel's asking what atmospheric carbon dioxide concentrations correspond to the triggers for Snowball Earth formation?
Yeah, that's a great question, and the answer to that changes a bit through time, because the sun has been changing how much energy is coming out through time. So it was fainter in the past, and so in the past it would have been at sort of higher CO2 levels to have a equitable climate, or a sort of and these sort of processes sort of can balance out CO2 at appropriate levels. So there's a lot that you sort of see this in climate models, and Earth ends up being largely self-regulating. So today there are some research that's been trying to do this. What would it take on Earth today? And I think it's on the order of something like 50 ppm, 80 ppm, something like that. So quite low. But those would have been higher in the past, probably back where Seth's about to talk about. It's more at a couple hundred, few hundred ppm. As a sort of calibration today, we're at around 410 ppm CO2 in the atmosphere.
Thank you, Nick. Well, we'll go ahead and transition to the next speaker, and really appreciate the questions from the audience. And sorry, we can't get to all of them, but it's such a pleasure to introduce Seth Finnegan. He's an associate professor in the Department of Integrative Biology, and also a curator in the Museum of Paleontology. His work revolves around understanding the paleo environments of marine ecosystems and their relationship to mass extinction. Seth's lab focuses on the processes that have shaped the composition of marine biota and the development of marine ecosystems from the origin of animals in the late Neoproterozoic, so billions of years ago, to the present today. Tonight, Seth will be talking primarily about his lab's work on understanding the causes of one of the first major mass extinctions that follow the evolution of animals. It's the late Ordovician mass extinction. So Seth will highlight that, and we look forward to your presentation, Seth.
Okay, fantastic. Well, thank you so much, Lisa, for the introduction, and thank you all for showing up. And before I get started, the first thing I want to say is just that the work I'm going to present is largely the product of the past and ongoing efforts of a fantastic and incredibly creative group of graduate students that I've been lucky enough to have here in my going on 10 years at UC Berkeley. I won't have time to highlight all of their efforts individually, but I'm very lucky to have had them. We're very lucky as a university to have them. So I'm going to start by just talking about why is it our group studies the marine invertebrate fossil record, right? So these are things like clams and corals and snails and extinct groups like trilobites. And you might be wondering why study this marine record? Because probably most of you, when you hear the word fossil, you don't think of things like that, or you don't think of these humble clams on the right. You think of the spectacular T-Rex on the left, which for those of you who know campus is in the atrium of the Valley Life Sciences building here on campus. And I love T-Rex as much as anybody else, but I'm going to make the case that actually we can learn as much, or I would even argue in some cases more, from studying these humble clam fossils, particularly if we're interested in the causes and the consequences of mass extinctions during which groups like T-Rex become extinct. And that's for a couple of different reasons. One of them is simply that marine invertebrate fossils are very abundant in the fossil record compared to fossils of large terrestrial vertebrates like T-Rex. So if you wanted to find a T-Rex, you'd first of all probably want to team up with Paul, who's done some work in the areas where you find them, and go halfway across the continent to Montana or Alberta. If you want to find clam fossils like these, you can get in your car and drive 15 minutes and find them in the Berkeley Hills. Another 45 minutes, you can find particularly nicely preserved ones here on the coast along Santa Cruz. These are 6 or 7 million years old. So if we're interested in evolutionary dynamics, they provide a much more complete fossil record than that of big spectacular things like dinosaurs. The other thing about the marine invertebrate fossil record that's really important and really special is that we can learn about the biology and the evolution of these groups from the morphology of their fossils in the same way that we would with the T-Rex. But they also preserve a huge amount of really important information about environmental change and climate change through time. And that's because as these shells are grown and precipitated from seawater, they lock in their chemistry, particularly in the form of stable isotope ratios of different elements, information about the ambient temperature, the salinity, the pH, the amount of dissolved oxygen, even the state of the global carbon cycle at the time that they lived and died. And so my group works this record from both angles, extracting both biological and environmental information from the marine invertebrate fossil record to try and better understand, again, the causes and consequences of mass extinctions. So this is a figure that summarizes many thousands of fossil and geochemical observations by many different researchers into a picture of Earth's changing climate over the past 500 or so million years when animal life has been diverse and abundant. And so the colored bars indicate the climate state through time. And that's again primarily from the geochemical composition of fossils. That is our primary archive of climate through time. And then the gray lines here indicate extinction rates. And you can see, of course, that there have been not just one, the end Cretaceous mass extinction that you're going to hear about from Paul, but in fact, several very large major mass extinction events. And you can see that some, but not all of these, coincide with major changes in Earth's climate state. So if we want to, there's certainly, obviously, there's a basic science question involved in just understanding the nature of this relationship. And also, of course, as we go into our current era of rapid anthropogenic climate change, we can't understand likely extinction risk among existing species without understanding the things that have caused species to become extinct during past episodes of rapid climate change and extinction. And so I'm going to talk in the next couple of minutes just about the work that my group has done on the first of these, the late Ordovician mass extinction event. So this is an event that occurred about 445 million years ago. And it coincides, as you can see here on the panel on the left, with an episode of relatively rapid and dramatic but short-lived cooling, probably driven, as actually some of Nick's work has shown, by some of the same silicate weathering mechanisms that he discussed. And this coincides with about 80% extinction of animal species on Earth, including heavy losses in all of the groups that you see figured here in this sort of classic museum diorama here. This is before there really was much in the way of animal life on land. We don't know much about that record. So if we want to better, now just to go back for a second, so you can see that this coincides with cooling, but subsequent glaciations have not coincided with major mass extinction events. And there's a lot of open questions about whether or not cooling itself is a major part of this extinction or it's just a coincidence. And so to better understand this record, we've been going for the last 10 years to a particularly well-preserved record, a place called Anacostia Island, which is today in the Gulf of St. Lawrence in subarctic Canada, but in the late Ordovician was located near the paleo equator at very low latitude. And this is a spectacular record that preserves about 15 million years of Earth history before, during, and after the mass extinction event in the form of a thick sequence of limestones that are about 1 kilometer thick. And it's not just complete, but extremely fossiliferous. So these limestones are largely made out of marine invertebrate fossils. If we go and pick up one of these, you can see it is composed largely of fossils. And so if we collect in a typical 20-pound sample bag, we will have thousands of individuals to examine later. So what we do is we go out, we collect lots of fossils, and our first priority is to understand the distribution of species in space and in time, to understand the habitats that they preferred when they existed, when they first came into existence, and when they last appear and became extinct. And so you can see here, this is us collecting. On the left, this is a graphic log, sort of a cartoon of different formations representing different sedimentary environments through time. This is about 100 meters of section, representing about 1 million years of Earth history. And you can see that many of the species here have their last occurrences just below or within this particularly distinctive bed here called the La Framboise member. The other thing we do, like I said, is collect some of these fossils, bring them back to the lab, and analyze their chemistry to try and reconstruct environments. And that's not quite as straightforward as it sounds, because as you can imagine, in 500 million years, fossils can undergo a lot of chemical adventures. So a lot of what we do is analyze them to try and select the ones that are best preserved and will give us a more primary signal. So you see here, we take, for example, this fossil rugose coral. It's a group of extinct corals, section it, and then do elemental mapping to try and better understand how it has or has not been altered. Take the best preserved ones and produce time series like these. We can see when we look at this same level, we see evidence of a major perturbation of the global carbon cycle, large-scale cooling and growth of ice sheets as large as or potentially exceeding the size of the ice sheets that Nick showed during the last glacial maximum, and considerable fluctuations in dissolved dissolved oxygen. So the correlation here obviously is highly suggestive, but of course correlation doesn't equal causation. So how do we try and get at causation? And the way we do that is primarily by looking at patterns of extinction selectivity. That is, we use models to try and generate the patterns of extinctions that we would expect to see across different groups and different regions, different habitats, under different possible scenarios, both of the kind of environmental change and which aspects of that environmental change matter most to the marine organisms. So, for example, the pattern that we see that is quite characteristic and distinctive for extinctions in the late Ordovician versus extinctions before and after is that species that had relatively limited paleolatitudinal distributions were at much higher risk of extinction than those that weren't, and species that were limited to relatively deeper waters were at much higher extinction risk than those that ranged up into shallower waters. And modeling efforts show us that these are exactly the sorts of patterns that we expect if, in fact, cooling itself, but also associated changes in bottom water oxygenation and paleoceanographic circulation were major agents of circulation, right? So we're able to use these patterns to causally connect the climate changes and environmental changes we're seeing to the pattern of extinctions. Okay, so that's just one example of the kind of event we work on. The broader period of time that we tend to work on, the early Paleozoic, is very rich in terms of having multiple changes, both in climate and environment and biodiversity changes. We work on a number of those. We also, I just want to close by saying, have a more sort of forward-looking part of our research agenda, which is that obviously there's a pure science aspect to this. We also want to know if we can apply some of this to better predict the taxa that we might expect to be at risk during the face of current anthropogenic climate change. And so another thing we could do is look at, for example, what are the factors that have been most predictive of extinction risk among different marine groups for the last 20 million years of the fossil record, when most of the modern groups we're interested in have been around. And then, look, froze there for a minute, sorry. As we've done here, project those onto the modern marine fauna to try and provide a longer term, deeper time context for ongoing marine conservation efforts and planning. And I think that is where I will leave it with, oh, I froze just for a second, whoops. Go back with a beautiful sunset picture from Anacostia Island, and thank you all for your time.
Well, that was terrific, Seth, and what a beautiful place, Anacostia Island. Why in that particular stretch of area, Nova Scotia, are the exposures so ideal?
Well, that's actually a great question, and it's interesting. You know, having grown up in the Northeast, right, you don't normally get exposed rock like that, or like the cliffs behind me here, which are also on Anacostia Island. And the reason we have this very good record of a late Ordovician glaciation is actually due to the much more recent glaciation that geologically speaking happened just yesterday. And the reason is this whole area was under an ice sheet. And basically that caused the crust to get sort of dunked down a little bit deeper in the mantle. And as the ice sheets melted away, the land surface has bounced way up. And so those cliffs are basically the signature of a coastline that is still rapidly uplifting. But unlike the uplift that we see all along the California coast, it's fundamentally driven not by plate tectonics, but by this post-glacial isostatic rebound.
Well, as we know from the record of deep time glaciers and more modern ones, they leave such dramatic signatures on the landscape, you know, one way or the other. There's a question in the chat where Rick Reeder, member of the audience, is asking for more detail about the extinction risk chart. What are the scales on the chart? And the
yeah, good question. So going like this one. Yeah, so this is what this is actually showing is the marginal effect on extinction risk. So this is actually not raw data, but this is output from a statistical model that tries to account for multiple different predictors that some of which are correlated with one another. And so this is the marginal effect, meaning kind of holding other things constant that are also varying. What is the relative effect of difference in that predictor on extinction risk? So these are actually two panels of a much bigger figure that shows a whole bunch of other possible predictors. And so what you see is that some of the other predictors that we look at have a much smaller relative influence, meaning we've centered all these lines around 0.5. Meaning something that has no influence as you vary it, there's going to be little or no variation along the y-axis. But these are all rescaled to kind of maximum influence. I have another figure buried in some slides afterwards that show the raw data that I'm happy to show if anybody really wants to dig in on the details.
Terrific. Well, we'll go ahead and transition to the next speaker, and there continue to be some great questions coming in. Maybe several of them we can draw from at the end of the presentations. There is a question about accurately dating rocks when they're sedimentary, so certainly using fossils, but this is a nice transition to Paul Rennie's talk on geochronology and really being able to probe the accurate ages of units. So thanks again, Seth. And it's my pleasure to introduce Paul Rennie, a professor in residence and director of the Berkeley Geochronology Center. His research focuses on the processes governing the evolution of planet Earth and its inhabitants using the tools of geochemistry, geochronology, and paleomagnetism. Recent interest areas include continental flood basalts and plume-related magmatism, mass extinctions, human evolution, and calibration of the geological timescale. So Paul has a really great span of topics included in this research, and we're really excited to hear from you, Paul.
Great. Well, thank you, Lisa. Thank you very much. Let me just get set up here. Okay, so I'd like to begin by acknowledging the very important contributions of a number of my PhD students and postdocs over the years. We've also had a lot of undergraduates involved in this various aspects of this research. They're too numerous, unfortunately, to show here, but everybody has contributed a lot. So when we talk about mass extinctions, you've seen several versions of diagrams much like this. This is a little bit different in that it's not showing extinction rates, but it's showing the number of families in the marine realm over geologic time, going from the Cambrian up to recent times. And I'm going to use a laser pointer here. So what you're seeing here is when you see major changes in the diversity or the number of families, that corresponds to a mass extinction. And so Seth talked about this one over here in the late Ordovician, and I'm going to be at the other end of the spectrum here at the end of the Cretaceous, the beginning of the Cenozoic era. So this just depicts marine animals, and here are some of the victims of the extinction. This is a foraminifer, and many of those went extinct. Many ammonoids went extinct as well. Actually, all ammonoids went extinct. But what most of you are used to hearing about is the dinosaurs. This is exactly the same dinosaur that Seth showed, the T-Rex in Valley Life Science Building. And it was really the demise of the dinosaurs that liberated the terrestrial ecosystems for mammals to flourish. And they just radiated into the vacant ecospace and took over. So here's an example of one of the very early mammals. This is actually believed to be a stem primate, and it comes from almost exactly just after the extinction level. So in many ways, humans ought to be grateful that the dinosaurs went extinct. So it's hard to talk about the Cretaceous Tertiary mass extinction without paying tribute to Walter Alvarez and his father Louis, who discovered in the late 1970s the evidence for a major planetary body having impacted the Earth. And this was, I would say, probably the biggest breakthrough in understanding why the fauna and flora, to some extent, changed so abruptly over a very, very narrow interval of time. Basically, this layer of rock represents the transition. And the Alvarezes found that this layer contained a very high abundance of iridium, which is rare in most earthly rocks, but it's abundant in certain kinds of meteorites. So that really opened up a completely new way of thinking about major changes in Earth history. And their hypothesis was somewhat slow to gain traction, but it gained increasing acceptance in the scientific community. And about a decade later, in the early 1990s, a major impact structure was discovered and studied in various ways in the northern Yucatan Peninsula of Mexico. And this really just completely solidified the impact theory. One of the consequences of the impact is that the target rocks in this area were subjected to melting and even vaporization, and were distributed very widely around the region. Here's a picture of a deposit of these little melted blebs, we call them tektites, in a small island off the coast of Colombia in South America, which is about 2,000 kilometers away. And it turns out that these are very nice objects, nice materials for dating by the argon-argon method, which is one of the techniques that I use. And so we've been able to date these tektites, and thus, because the time between when they were formed and when they were transported ballistically to Colombia is insignificant, we can date the impact. So that's how we know the age of the impact in absolute terms, not just in terms of relative age. And if we want to know when the dinosaurs went extinct, well, it turns out that the best place I know of to discover that is in an area of northeastern Montana, where there's a very nice, well-exposed sequence of sediments that were deposited in lakes, streams, floodplains, in other words, a range of terrestrial environments. And one of the nice things about these strata is that below a certain level, which turns out to be the boundary, the extinction level, you find dinosaurs, you find T-Rex, you find Triceratops, various other dinosaurs, but those are really abundant in the latest Cretaceous. And above this horizon, nada, no dinosaurs whatsoever. And there are other changes in the taxa across this boundary. But fortunately, within that layer, which is a coal bed, and there are numerous other coal beds in these sections. Here's another one up here. But down at this level, as in other places, there are layers of volcanic ash, similar to what both Seth and Nick have described, that are amenable to dating. And in this case, just below this volcanic ash, there's a very thin layer. You can barely see it, but it's right here, about a centimeter below the ash, which is the white layer. And this contains tektites, it contains shock quartz, it contains high concentrations of the element iridium. So, and it's unique in the section. There's nothing else like it. There's only one of these layers that contains iridium and other elements anywhere in the world in any given section. So we can confidently date that now. So we've dated the extinction, at least of the dinosaurs. There's more to the story, as it turns out. In the past, I would say most importantly in the past 10 years, it's become very clear that many of the major peaks in extinction rate, and this goes back, you've seen versions of this kind of slide several times now. It turns out that many of the mass extinctions that we know about over time correlate with what are called large igneous provinces. These are huge piles of lava that cover very large areas of the Earth, and they seem to have been erupted in really brief time intervals. So by comparison, the impact at the KT boundary 66 million years ago is unique. There's, at least in terms of what we know about, credible evidence for an impact. This is the only one. So in a generic sense, massive volcanism seems to be very easily or very straightforwardly related to mass extinctions and other kinds of ecological crises, which I'm not going to go into right now, but some of them are shown here. So how does volcanism cause or induce ecological change? Well, it's about climate. And most scientists who study these things believe that it's really the volatile elements, that is the gases that are emitted by volcanoes, that induce climate change, namely the greenhouse gases like carbon dioxide, methane, and water, most importantly carbon dioxide, induce warming, and another category of sulfur compounds that become aerosolized induce cooling. And those then trigger a whole spectrum of related effects, which are very complicated, and there are lots of feedbacks, and I really don't have time to go through all of these, but it's pretty clear that climate change is what has driven the extinction of the dinosaurs and all of their cohabitants. So let's drill down now a little bit and look at the Deccan Traps of India, which is the one that occurred at around the KT boundary time. So this is a massive, large igneous province. It covers a significant part of peninsular India. And that's today. The original extent before erosion was probably much broader. The Deccan Traps consist of just a huge pile of lava flows. These are just nothing but lava flows, which reach a cumulative thickness of about 3 kilometers. And the overall sequence has been divided into a number of different formations that are named and shown here, divided by different geochemical characteristics. So the compositions of these lava flows within each of these formations is different to some extent. The biggest difference occurs right here between this bushy formation and the Polod Port. So keep that in mind. And we've been able to date a large portion of this sequence of lavas. What I'm showing here is dates that come from 2 different techniques. One is the argon-argon method, which is all of these are from my lab. And the other is the uranium lead method that is shown in these red triangles, which come from a group at Princeton University. And I'm just going to focus on the argon-argon results because the uranium-lead results are frankly quite a bit scattered, and they require a great deal of interpretation, and they're not actually derived from the lavas themselves. So that requires a bit more subtlety. But the argon-argon data are pretty straightforward, and pleasingly, they go from oldest at the bottom to youngest at the top. There's a lot of overlap. In some places, the uncertainties are quite large, but we can say that the total span of volcanism was something on the order of 1 million years. And the KT boundary as dated by argon-argon is somewhere in this interval, right? That's where this curve crosses the KT boundary. So if we look at that in the context of climate, and I'm just going to show one climate proxy here, which is marine temperatures as inferred from oxygen isotopes in certain microinvertebrates, using the kinds of techniques that Seth talked about. You can see that the onset of Deccan volcanism, which occurred right about here in time, about 66.3 million years ago, coincides with a period of rapid temperature increase by something on the order of 3 to 4 degrees, which is huge. For the oceans to undergo that much warming over something about 50,000 years is a pretty significant event. And then we see this decline in temperatures. In fact, the temperatures go down to below where they started out just beforehand. This is probably an example of what both Nick and Seth talked about, but mainly Nick. And this is the drawdown in CO2 that is associated with weathering. So you've erupted a bunch of lava, which is, as was pointed out previously, the kind of the ideal sink for carbonate because of its richness in calcium, magnesium, iron, and so forth. So you have the ideal repository for CO2. And there seems to be some overshoot. Some of this cooling may be due to the release of sulfur aerosols as well. But one of the things I want to draw your attention to is that I haven't talked about this yet, but these color-coded bars correspond to the different formations. Their durations are shown on the horizontal axis. The heights of these bars aren't related to this scale. They're just relative indications of the volume of these formations. So what you see is right at the boundary, there's a very significant increase in the volume of lavas that were erupted, very dramatic. And so what we actually think, notice that coincides with the impact within our uncertainties. And so that has led to the hypothesis, which was really first formulated by Mark Richards, the former Dean of Physical Sciences here. And this is an hypothesis that we're still involved in testing. It's not thoroughly redeemed, but it's not disproven at this point either.
Paul, I'm so sorry to interrupt. We're at time.
Okay.
So you want to wrap up? Do you have one additional slide or?
Yeah.
Okay.
All these phenomena are indistinguishable in time: extinction, impact, and the Deccan transition. So the question is, do we have to choose between asteroid impact and massive volcanism as triggers? No. I mean, there was a time when that was sort of the mantra, is that it was one or the other. But no, we don't have to. Both almost certainly contributed, and they may in fact be genetically related. Thank you very much.
Great. Thank you. Thank you. Well, I'll pull a question from the chat. Tom McCloskey asks, if volcanic events drive extinction, how does the magnitude of these events compare to the anthropogenic CO2 in the 20th century?
Well, the estimates for how much CO2 volcanism produces, and I think we have to keep in mind that one of the things we're learning is that the CO2 that is put into the atmosphere in general by volcanism is not just produced during eruption. CO2 basically leaks out of the crust when you heat the crust by putting a bunch of hot magma into it. And some of that CO2 is actually derived from sediments, from degassing of sediments. So the point is that at present, what are we at? About 420 ppm CO2 in the atmosphere. Most estimates of how much CO2 volcanism was responsible for are significantly higher than that. That's in a nutshell.
In a nutshell. Paul, you said something that I want to highlight and ask each of the speakers to comment on, and that is there's always more to the story. You know, given the nature and process of science, there are discoveries and new findings that may drive your research in a different or unexpected direction. So besides your own core areas of geoscience, if each of the speakers could share an example of what's happening in related research that inspires or influences your own work. So Paul, if you want to answer that first, then we'll go to Seth and Nick.
Okay, I've been asked to stop sharing my screen, and I believe I have stopped, right? Okay, I'm sorry, Lisa, but could you repeat the question?
Sure. There are, of course, unexpected discoveries and findings in science. There's many parts of our science that are influenced by what's happening in other areas of research. So what's inspired you? What continues to inspire and influence your work that may be happening in other areas of geoscience?
Yeah, well, my research personally is very dependent on the technology of geochronology, which is basically the province of nuclear physics. And so I benefit tremendously from interactions with our nuclear engineering department. We have lots of collaborations with those folks, and we're perpetually striving to improve the accuracy, the precision of the dating techniques. And I mean, the kinds of data that both Nick and Seth showed you for geochronology are fabulously precise compared with where we were just 10 years ago. And so this is a technique that is just always advancing, and that because geologic time is so important in these sciences, I have to say that's really the area that I see just being a dramatic improvement.
Yeah, I guess I'll sort of piggyback on that by saying there was someone in the chat who was sort of asking, hey, how can you date these rocks if they're sedimentary rocks? And I sort of tried to highlight that, sometimes you need to get lucky in certain types of sedimentary rocks and you have particularly in the rocks I'm often that are working on, which are before the evolution of animals and that fossil record to date them. But yeah, our ability and the sort of progress of the community to tell time in ancient Earth history has really advanced a lot. And some of what Paul was highlighting about those timescales of these large igneous provinces, and it's been a major find how rapid a lot of that emplacement is, which then really gets you at the rates of those gases coming out into the atmosphere. More broadly, I mean, what's so exciting about studying Earth science, right, is you're trying to think about how all these different dynamics of the Earth's interior and its surface and its atmosphere are interacting with each other to drive global change. And of course, we're very motivated on in our department, people are studying modern climate, and there's been lots of questions coming into the chat about how we can think about what's happened to this past as analogs for the present. Of course, there's all this basic science, just sort of fascination with how did our planet, how has it become this habitable place on which our species evolved and is able to thrive. But it's all these sort of interactions between all these different disciplines to try to understand our dynamic Earth through time, including between the Earth and Planetary Science Department and Integrative Biology. So over to Seth.
That's for sure.
Yeah, so I'll sort of continue to piggyback on both of those and say, once again, I mean, the dating is absolutely fundamental to everything we do, and continues to be the driver of major advances. And as Nick pointed out, so I'm actually, even though my background is primarily in geology, all of my degrees are geological sciences, and before I came to Berkeley, I was always in geology departments. At Berkeley, due to the history here, the paleontologists have mostly been in the Department of Integrative Biology. So with evolutionary biologists and ecologists, and that's actually, probably where, for me, the maybe unsurprisingly, the most exciting, interesting synergies have been in the last 10 years, and not just on campus, but one of the slightly grim ironies of the present is that a lot of the processes that were probably really important in driving extinctions in the geological past are beginning to play out in our oceans. And the extent to which they will play out is still very uncertain, right? That's uncertain partly because of things we don't understand, and it's uncertain partly because of things we don't yet know about our future actions and their effect on things like ocean temperatures, ocean acidification, deoxygenation. But we've learned a tremendous amount from studying, again, particularly how marine organisms are responding to incipient warming and deoxygenation and pH changes. And so that's slightly depressing, but also, there is a reciprocity there between the biology and the deep time record that is very interesting and starting to really, I think, shed light in both directions.
Right. Well, thank you for that. What a really wonderful series of talks. And I'm going to hand the floor over to Mike Botchin, the Dean of the Division of Biological Sciences. And again, thank everyone for listening. And we're sorry we're able to get to all of your questions, but Mike, take it away.
Okay, well, thank you, Lisa, and thank you, Nick, Seth, and Paul, for sharing a glimpse into mass extinctions and ancient climates. It certainly puts a lot of things into perspective. One of the best parts of this event series is hearing the excitement conveyed by the scientists and faculty. I love a good science talk, and it's the thing I most want to hear about while working as a dean. It sparks my intellectual curiosity, and it sparks hope to think that fantastic minds pondering over and working on such science questions actually make huge contributions to our civilization. In the upcoming months, we plan to host a number of unique field trips with select faculty and student research groups where alumni and friends can join us. Please watch for future invitations to become a participant. I want to thank you for all of us who are here for joining us, and encourage you to reach out if you like to learn more about anything we've covered. We'll be sharing additional resources with you by email about today's topics and speakers, and a video of today's session will be available at basicscience.berkeley.edu approximately a week from now. We look forward to seeing many of you at our next Basic Sciences Lights the Way event, which will be called The Future of Quantum Materials on March 22nd, and our IB field events. Until then, stay curious, fiat lux, and go Bears.